Hello, my name is Nick Kelly,
I'm Sean Labuda.
And I'm Nate Holder.
and our senior project is on manufacturing of rotating bag buckles. A little bit for the background, last fall, Matthew Jensen approached the IME department with a senior project idea. Matthew is a local entrepreneur who used to work at the Hot House Startup Accelerator in downtown San Luis Obispo and now lectures for Cal Poly's architecture department. He has broad experience working in mechanical design and contracting for companies such as Intel. He is ready to begin the first runs of mass producing his product, but does not know where to start.
A little bit about the product. Matthew's product is a patented rotating plastic buckle, ideal for messenger bags. The design brought to us consisted of 4 different components: a hook, which slides into a retainer, which is then attached to the bag using 2 screws that are fastened into a metal backing plate. The buckles are currently 3D printed using 100% pure nylon, while the backing plate is laser cut and hand punched and threaded to allow the screws to attach to the retainer. As you can see here, the hook slides into the retainer and they can freely spin 360 degrees. To release the hook, you simply press down on the center and slide it back out.
Matthew's current method of manufacturing, 3D printing, the hook and retainer, and laser cutting, flaring, and tapping the backing plate costs roughly $16 per buckle. This is much too expensive to be competitive in the backpack market, where buckles are typically produced cheaply and quickly in China. This became our problem statement.
So our task was to determine how we can manufacture these buckles here in America. This is very important because in order to protect the intellectual property that protects the buckle, that being Matthew's patent, it has to remain in the United States. The goals for this project were to determine how to manufacture the buckles here on a larger scale, evaluate product design for improved manufacturing and assembly, and explore possible material options for the product, as well as providing an economic analysis of these manufacturing possibilities.
Diving a little deeper into the deliverables, Matthew wants to create 2,200 buckles to attach to 1,000 bags, which is a standard order size from China, at a price point of around $4. How to do this? First and foremost, the design for manufacture had to be reassessed so that our objectives would become feasible. The buckle was to be redesigned to exclude the unnecessary aspects of it. Reducing the design down to the necessary pieces and reducing the non-value added parts are a key part of design for manufacture and assembly, and a proven way of reducing cost. A new method of manufacture also had to be researched so that the buckle could be manufactured in a timely manner with a great reduction in cycle time. The long cycle time of 3D printing, not to mention the additional labor for the backing plate and fasteners, made the current process too lengthy to be appropriately mass manufactured. A material that would be high in strength, low in cost, and easily manufacturable are the key components for our material selection. The material must also be able to withstand weights in excess of 160 pounds for it to be appropriate in our product.
For design, the team decided to remove the backing plate and screws by applying design for manufacturing and assembly principles. By implementing ultrasonic welding directly to the nylon straps, which could be sewn onto the bags easily, this would reduce the total number of parts to be manufactured from 5 to 2. Matthew helped redesign the hook and retainer accordingly, creating a 1-inch hook to better fit the common 1-inch nylon strap used for bags, as well as a retainer without holes for screws, leading to a smaller part footprint and less required material.
Our team used SolidWorks mold tools in an attempt to develop 3-dimensional molds for both the updated hook and updated retainer. Unfortunately, the transfer of the parts from Rhino files, where they were originally designed, to SolidWorks caused numerous errors that would not allow for proper mold splits for either part. Our team still wanted to understand the process of using the mold tools in SolidWorks, so we were able to create very similar products that had a similar geometry from the ground up to help eliminate the transfer errors. The second method worked, and molds were created successfully. However, the mold shutoff surfaces could not be easily machined, and other methods for the mold design had to be considered. Our backup method created solid blocks around the part to extract and split the mold manually after the core had been removed. This method worked much better, albeit not a typical method for mold design, and gave us a much better idea of what the molds for these parts would look like in the finish.
Continuing on, we developed various ultrasonic weld energy director layouts for possible strength testing. This way we could set up a failure analysis on each of the various layouts to determine which one offers the strongest weld strength. Nylon 6/6 was chosen for the material due to its ability to be molded into a high strength yet durable product, and its widespread use and low cost makes it an ideal candidate for injection molding that will stand up to the rigorous demand needed in our product. In addition, this type of nylon is very adept at being ultrasonically welded to other types of nylon, such as our strap, and is quite suitable for our project.
As far as methodology, Rob Swanland is a local engineer at Unibox Enclosures, an injection molding manufacturer that Matthew has built a relationship with. He offered us advice on mold design and material selection. With our completed mold designs, we sent them as step files to Rob for review. With his experience and knowledge of the molding process, he recommended and helped us implement some changes to the mold designs. The new design is shown here. Additionally, we created layouts for the ultrasonic welding energy directors. These designs were also presented to Rob, and he offered us his thoughts and suggestions. Our initial idea would send multiple parts with different energy director designs to Branson Ultrasonics in Massachusetts, to weld the various designs and strength test to determine the best option. However, this option would require different molds sets to create different energy directors, which cannot be justified for investment.
As for the economic analysis, the key factor in deciding to look at injection molding as a means to mass manufacture the buckles was the economic benefit to the price per part. The 3D printing price of $16 per buckle was much too much for Matthew's vision of having 2,200 buckles made. That would be a total cost of $35,200. After sending in the mold designs, 0 Hour gave us quotes for both aluminum and steel molds. With aluminum molds, which were quoted at about $2,400 total for both hook and retainer, the price per buckle drops to $241, which would be $5,302 total for the 2,200 lot. The steel molds, on the other hand, were priced at $4,900 total for the molds and gave us a buckle price of $3.59 per buckle, leaving us at about $7,900 total for the 2,200 lot. These prices include material estimates of 42 cents per buckle and labor estimates of 82 cents per buckle found through our research. By investing in injection molding, Matthew can save roughly between $27,000 and $30,000 depending on the mold type chosen.
Our results and recommendations. From the results of our project, we found that injection molding is the most feasible way for Matthew to create 2,200 buckles for his prototype bags. From further discussion with Rob and Matthew, our group believes the best course of action will be to create a steel mold with steel-safe max material condition. Branson helped us to decide on the continuous ridge energy director, stating that the design would work well with our application. Additionally, the max material condition on the mold would allow for us to cut the ridge larger, more nylon, if we tested smaller ridges first and they weren't as strong as we wanted them to be. The decision to make the more expensive mold comes down to quality of mold and tool life. The steel mold provides a higher strength material for the molding process, which will offer a longer tool life and the ability to produce more parts. This will be a key factor as Matthew begins to scale up his business, making more buckles for his bags. The next step for this process is to have the molds tooled and to begin the first run of parts. These first few parts can then be sent to Branson for the ultrasonic welding with different materials, both fiber reinforced and unreinforced nylons. Following the welding, hole testing will offer Matthew an idea of which material should be selected, as well as if more material in the energy director would be required.
In our conclusion, from this project, our group experienced the process from design to manufacture of plastic injection molds. We applied our understandings of design for manufacture and assembly to a unique part that provides both an aesthetic and ergonomic value to the customer. Additionally, we learned the mold design process and applied it to parts in SolidWorks. We struggled with troubleshooting part type file conversions, which forced us to our contingency plan of creating the molds via blocking methods. However, with the advice of experienced professionals, the mold designs were completed and quoted at a price that enables Matthew to successfully continue his project of bringing the buckles to market.
Thank you for your time, and we look forward to any questions you have.